Hello. In this video, I will go over the basics of vectors. First, we need to start off with a definition. A vector is a mathematical object that has length, also called magnitude, and direction. It looks like an arrow. So for some examples, we could say this is a vector, this is a vector, this is a vector, and so on. Okay, you can draw any arrows are vectors. Okay. What are vectors used for? Vectors typically represent movement, or a force. Okay. So what we're going to start off in terms of looking at vectors is we're going to start off with some geometric attributes of vectors. And then once we're done going over those geometric attributes, we'll go over some algebraic attributes. The first geometric attribute we're going to look at is equality. The way that you can tell the two vectors are equal by looking at them is by checking to see, do they have the same length and do they have the same direction? Okay, so just for example, let's say we had that vector as vector A, here's vector B, here's vector C, here's vector D, and there's vector E, right? So we said this one's A, B, C, D, and E. So which two vectors, just visual inspection, look to be equal? So to be equal, we want the vectors to point in the same direction, and they have to have the same length. All right, so which vectors have the same direction and the same length? A and E. All right, so vector B points in the same direction as vector A, but does not have the same length. C does not point in the same direction as vector A, and nor is it the same length. D looks like it has about the same length as vector A, but does not point in the same direction. And so only E points in the same direction. Okay. So the next thing we're going to talk about is addition. But in order to do that, we need to first go through and define some terminology for vectors. Okay, so let's say I have a vector. Okay, we'll say this is vector A. And so the terminology we're going to define is we're going to say that this point here is the initial point of the vector. And this point here is the terminal point of the vector. Okay. All right. So to go through now, once we've done that, we can talk about addition. So if we're going to go through and add two vectors, let's create two vectors that we can go through and add, and let's just put them off to the side so that we can possibly use them for subtraction and scalar multiplication as well. All right, so let's just create a couple of vectors. Let's say we've got vector A. Let's say that's vector A. And we've got vector B. Okay, and then so if we're going to go through and add vector A and vector B, the way that we do that is we start off by taking vector A and then putting vector B onto the end of vector A to kind of create a chain of vectors. Okay, so let's just draw that so that we make sure that we've got that down. All right, so let's just put over here. So our example for addition is going to be, so here's vector A, and then right on the end of vector A, right on the end of vector A, we want to draw vector B. All right, so there we've got vector A, and then we've got vector B. All right, then if you, to add vector A and B, what you do is you start at the initial point of vector A and draw a vector that ends at the terminal point in vector B when they're placed end to end like this. So if you take vector A and then place vector B so that the initial point of vector B is on the terminal point of vector A so that they've got this chain, then to add the two vectors, the sum is going to be starting at the initial point of A and ending at the terminal point of B. So this vector here, this is A plus B. Okay, so that's how addition works. Let's do one more example, and we can go through and create a couple more vectors that we could use. Let's say this is vector C, and let's do this as vector D. All right, so then in that case, what would C plus D be? To go through and figure out what the sum of vector C plus vector D would be, what you're going to do is you start off with C, you draw that, and then once you're done with that, you want to go through and take vector D and draw it. It looks about like that. And then there's C and D. Then the sum of C plus D is going to point from the initial point of C to the terminal point of D. Like that. So that's C plus D. Okay. So that's addition. Next, we're going to look at subtraction. So rather than me clearing out the whole page, I'm just going to clear out the stuff that's over here so that we can keep our vectors over here, these vector examples. Okay, so let's do subtraction. So the way that you subtract two vectors is you start off with vector A and vector B, and you have them start off where you take their initial points and you have their initial points start from the same place. So let's just draw that first just to make sure that that makes sense. So we're going to take A, we're going to put it, oop, not a line, it's supposed to be a vector. Let's take A, put it, and then next we want to go through and draw B. So you want the initial points to be the same this time. All right, so that's roughly vector B. All right, so we've got A, we've got B. So if we go through and subtract B from A, right, so A minus B, the way that you do that is you have the vector that points from the terminal point of B to the terminal point of A. Like this. This is A minus B. So the thing that can be helpful to remember this, so assuming you do remember when you go through to subtract that you have the initial points as the same, right? A and B have the same initial point, is that the one that's positive is the one where you end up pointing to. Okay, so you point from the negative to the positive. That's how I have it memorized, right? So A is positive here, so the vector points from B, which is negative, up to the positive one. Okay, so that's how you go through and geometrically figure out the subtraction of two vectors. Let's do C and D here just to make sure that we've got that. Okay, so again, we want to start off by having the same initial point. So we want to go through and draw C. And then we want to draw D, so the same initial point. So since this is the initial point of C, we want to draw D right there. Okay, and then from there, what we want to do is we want to have the, if we're doing C minus D, then we want to point from the end of D to the end of C, right? So this was D, this was C. So we want to point from the end of the negative one to the end of the positive one. So this is assuming we want to do C minus D, right? So if you have C minus D, then the C is positive, so that's where the arrow points to. The D is negative, so that's the initial point is at the terminal point of D. Okay, so that's subtraction. Next, let's look at scalar multiplication. And again, I'm just going to subtract, I'm going to erase these, and we'll just put the example on the same page. So the way that scalar multiplication works is you end up taking a multiple of the vector to represent the result. So if you start off, if this is A and we want to go through and represent 2A, then what we do is we just do A twice. So let's just say I want over here, I want to do 2A. So what we want to do is we just want to represent that, we're just going to do A twice. So you've got A, you can think about that. That's A once, and then we're just going to do A a second time. You know, or another way of thinking about it is it's a vector that's just twice as long and points in the same direction as A. So the way that I think about it is like we've got vector A is there twice. But another way to think about it is that 2A is going to have the same direction as A, but be twice as long. Those are the same idea. Okay, so that's how we go through and calculate scalar multiplication. So we can play around with these others. You could do 3B. So if we're going to do 3B, then what we want to do is we want to just do, there's B once, twice, I don't know, 3 times maybe. And so you could say that that's B 3 times. So there's B once, there's B twice, there's B 3 times, or something roughly like that. All right, so that gives a second example. And then the other thing that you cover with scalar multiplication is negatives. If you multiply by a negative, you end up with a vector that points in the opposite direction. So if we wanted to go through and find, say, negative C would be the vector that has the same length as C but points in the opposite direction. So this would be, that's about vector C right there. And then you can also have, of course, have negative vectors and a multiple as well. So we could have negative 2 times D, in which case you'd want to reverse the direction of D and then take 2 of those. So if we were to reverse the direction of D, then it would point this way. And if we did 2 Ds, something maybe about like that. And that would be 2D. Okay, so that is scalar multiplication. And that covers the basic geometric attributes of vectors. Next, we're going to move on to talking about the algebraic attributes. To do that, we're going to start off with some information to help ground us. So suppose we had coordinate axis, and we had a vector. Let's say this is vector A. And let's say this distance here is A1. This is A2. And we can go through and define vector A as being A1, comma, A2. Okay, so this enables us to go through and algebraically define a vector in terms of its coordinate pieces. So these are called the components. So the x component and the y component. Okay, this can be extended to 3 dimensions. So if we have our vector here, and let's say that vector is a little hard to see there, but if we went through and did a dashed line, and then another dashed line, and so we could, if we said that this distance here was A1, so you go A1 in the x direction, A2 in the y direction, A3 in the z direction, then we could say vector A is defined by A1, comma, A2, comma, A3. Okay, so this enables us to go through and define a vector in terms of its components in the x, y, and z direction. Let's look at a couple quick examples of that, which we can do over here off to the side. So if we had vector A was equal to 1, comma 2, then we could go through and draw vector A on a coordinate axis. It would be the vector that points 1 unit in the x direction and 2 units in the y direction. You can also have vectors with negative components. So you could do -1, -2. And if we did that, then if we had our coordinate axis, then the -1, we'd go 1 in the negative x direction and 2 in the negative y direction, and we would get the vector that points from the origin to the point -1, -2. Okay, so there's some basic attributes to get us started on vectors algebraically. Next, what we're going to do is we're going to go through and look at adding, subtracting, and scalar multiplication. But before we do that first, I almost forgot, we need to go through and talk about length. Okay, so length slash magnitude. So magnitude is another name for length of a vector. So let's suppose we have vector A equals A1, comma A2. Then the length of vector A equals the square root of A1 squared plus A2 squared. And we can go through and verify that that is a sensible definition by taking the information that we just looked at, right? So we could go through and draw a picture of A, right? So if this is A1, this is A2, and here's our vector. And the question was, what is the length of vector A? Okay, well, if you know this is A1 and this is A2, we could go through and just create a right triangle and use the Pythagorean theorem, that says that the hypotenuse, the length of the hypotenuse squared is going to be the length of the leg squared, the length of A1 squared, A2 squared, right? So you'd get the length of A squared would equal A1 squared plus A2 squared, and so the length of A equals the square root of A1 squared plus A2 squared. Okay, so the length / magnitude definition just comes right out of the Pythagorean theorem. Length and magnitude also can be extended for vectors that are in 3 dimensions. So I'll save you going through and drawing you a picture, but in 3 dimensions, we could say the length of A is the square root of A1 squared plus A2 squared plus A3 squared. Right, so that's be assuming we had a vector that was in 3 dimensions. Okay, so assuming we had the vector A is A1, A2, A3. Okay, so that gives us length and magnitude. We can go through and look at an example. Let's just sneak in an example over here off to the side. So if we had vector A is equal to 2, 3, and you're asked to go through and find the length or find the magnitude, the length of A is the square root, 2 squared plus 3 squared. So we get the square root, 4 plus 9, which is 13. Okay, so that's our definition for finding length and magnitude. Okay, now let's go over addition and subtraction. All right, addition and subtraction. So just like we did earlier with when we were going through looking at addition, subtraction, and scalar multiplication, let's go through and create some examples that we can look at. All right, so we're going to go through, actually, these are going to be specific examples this time. So let's go through and say that one example could be 1, 3, B could be 2, 1, and C could be -1, 1. Okay, so the definition for addition, algebraically, for addition of vectors is if we had vector, let's go through and say vector x is x1, x2, and vector y is y1, y2, then x plus y equals x1, x2 plus y1, y2 equals x1 plus y1, x2 plus y2. Okay, so the way that you go through and add 2 vectors is you add the components. So you do what's called component-wise addition. So we're going to take the x component from the first vector and the x component from the second and add them. And we're going to take the y component from the first vector and the y component from the second vector and add them. Okay, so I apologize for using x and y here because you get x component and y component, but I already used up a, b, and c. So let's go through and just do an example just to make sure that that's clear. So if we want to go through and add a and b, we would take 1, 3 and add 2, 1. So we would get 3, 4. And let's do another one. We could go through and do b plus c. So if we do b plus c, that would be 2, 1 plus -1, 1, which equals 1, 2. Okay. All right, so that's the basic method for going through and adding vectors when it comes to algebra. What we can go through and do is connect the two definitions just with a simple example. Let's go through and pick one of these. Let's pick this one. I think it's easier when the numbers are both all positive to just go through and verify that this definition links with the definition that we did earlier. Okay, so if we start off and we have a coordinate axis, all right, and we go through and take the vector 1, 3, so that would be 1, 1, 2, 3. So that's vector A. Okay, and now the definition that we used for addition earlier for geometric is we put the initial point of B at the terminal point of A. So we want to start here and then draw B. So knowing what we do about B, B is 2, 1. So from there, we want to go 1, 2, and then up 1. And we can draw vector B like that. Okay, so now we've got, there's A, there's B. Then what we should get, if we go through and take the initial point here of A and end at the terminal point here of B, we should end up getting, if we just count, we should end up getting the result over here that we got. So what is that? So it's going to be 1, 2, 3, 1, 2, 3, 4. Yes, it does work. Okay, so that is how we calculate A plus B. So you can see that the two definitions do link together, that taking the X components and adding them and the Y components and adding them is the same thing as taking A, taking B and putting it at the end of A and then just combining them into a single long vector. Okay, so that is addition. And let's look at subtraction next. And just like earlier, I'm just going to subtract this so that we can keep our examples. Did I say subtract? I meant erase. Subtract, erase, it's all the same thing, right? Okay, so if we have x minus y, that equals x1 comma x2 minus y1 comma y2. And just like with addition, to go through and calculate it, you're just going to do the subtraction component wise. So we're going to take x1 minus y1 to get the x component, and we're going to take x2 minus y2 to get the y component. Okay, and we can go through and do some examples here. So we could do A minus B equals 1, 3 minus 2, 1. And if we do that, 1 minus 2 is going to be negative 1. 3 minus 1 is going to be 2. And we could go through and do B minus C. And so that would be 2 comma 1 minus negative 1 comma 1. And if we do that, you get 2 minus negative 1. That's going to be 2 plus 1, which is 3. 1 minus 1, that's going to be 0. Okay. So that's a simple way to go through and subtract. You just like with addition, you can go through and verify that this definition does fit with the one that we did earlier. Let's go through and do A minus B again. I think, again, it's maybe a little bit easier if the values are positive. Okay, so when it comes to subtracting, we want to have the vectors have the same initial point. So we want to go through and draw the vector that goes from the origin to 1, 3. So that would be 1, 1, 2, 3. That's going to be vector A. And then we want to go through and draw vector B, which is the vector 2, 1, right? So that's going to be 2 over and 1 up. That gives us vector B. And then, if you recall, When we subtract vectors, we want the vector that points from the end of the negative to the end of the positive. So we're going to get this vector here. And if we just go through and count, we should end up getting the same result that we did here. So this vector here, we ended up going 1 to the left and then up 2. 1 to the left, that would be -1, 1 in the negative x direction, and then up 2. All right, so it does work. Right, so that'd be A, B, and then A minus B. Okay, that is subtraction. Next, we have scalar multiplication. And again, I'm going to just erase all of this and put our scalar multiplication right here. Oops, I forgot that I was not going to erase our definition. So we have scalar multiplication. And let's stick with x. We have x. X is x1 comma x2. Then if we're trying to find a scalar multiple, which we're going to use letter k for generic scalar multiple, this would be k times x. To go through and calculate that, we do k x1 comma k x2. So when you do a scalar multiple, you take the scalar and you multiply it by each of the components, by both of the components. So if we wanted to go through and calculate 2a, that would be 2 times 1 comma 3, which would be 2 comma 6. We could do 3b, which would be 3 times 2 comma 1, which would be 6 comma 3. You can do negatives. We could do negative c. That would be negative 1 comma 1, which would be 1 comma -1. So those are all examples of scalar multiples. And just like with the others, you can check that this does match with our definition from earlier. If we've got A is 1, 3, so let's say that's A, then 2A is going to be 2, 6. So if you take, there's A, and then you go through and do a second A, right? Then you end up at this point here would be 2 comma 6. So 2A is going to be A and then A a second time, which is what I said earlier. Okay, so it does end up matching up that if we wanted to find 2 times A, we would just double the components. Okay, so that is scalar multiplication. Next, finding a vector between points. So if we have two points, let's say we've got here is point P1 and here is point P2. And let's say this is the vector. And we can provide some coordinates. Let's say P1 is x1 comma y1 and P2 is x2 comma y2. Then the vector that points from P1 to P2, we could denote as P2, P1. So P2 is the terminal point, P1 is the initial point. And we could go through and subtract the components to find that vector. So we would go through and do x2 minus x1 and y2 minus y1. Actually, I think I have this reversed. It should be 1, 2. Okay, so that's how you go through and calculate that. And if you think about it, right, if you were to go through and find this vector, what you do is you would figure out how many x units there are to get this direction. So you'd figure out how much to go this way. That would be the amount of x, and then how much to go this way. That would be the amount of y. To calculate that x stuff, if we have this is if we have this is x2, and we have this as x1, then x2 minus x1 is going to be the length of this. And if we want to go through and calculate this y distance, then this is going to be y2, and this is going to be y1, and so y2 minus y1 gets you this distance. So that's the way that you can go through and kind of prove to yourself that this is the right definition to go through and subtract the components. Okay, so and this also works in 3 dimensions as well. Let's do a 3-dimensional example. So let's do, for an example, and we're not going to draw it, but let's say we have P1 is 1, 3, -2, and P2 is -1, 4, 5, and your goal is to calculate P1, P2. Okay, so to calculate P1, P2, you're going to subtract the coordinates here, P2 being the terminal point, and then P1 being the initial point. You want us to take P2 minus P1. Okay, so we want to go through and do P2 minus P1. So you want to do -1 minus 1, that's going to be -2. You want to do 4 minus 3, that's going to be 1. And you want to do 5 minus -2, that's going to be 7. Okay, so that gives you an example. You just subtract the coordinates. If you subtract the coordinates in the wrong direction, what are you going to end up with? All right, so like the mistake I initially had where I had the 2 and the 1 reversed, you'll end up with a vector that points in the opposite direction. So that's what will be the end result if you do that. Okay, so next we're going to look at unit vectors. So what is a unit vector? Unit vector is a vector of length 1. Okay, so that's just our definition. So anytime you hear the word unit vector, that's what it means. It means that the length of the vector is 1. So we're going to look at some coordinate unit vectors. So by coordinate unit vectors, what I mean is the vectors that point in the coordinate directions, right? So if this is the x-axis and this is the y-axis, and we have the point here that's at 1, 0, and we have this vector here, that vector is the coordinate unit vector in the x direction, and we call it vector I. Okay, and similarly, if we had this point here, and let's say that point was at 0, 1, and we went through and put the vector there, all right, and that vector, we call that vector unit vector J. Okay, so just off to the side here, vector I equals 1, 0, vector J equals 0, 1. Okay, so those are just special names for the coordinate unit vectors. The same idea also applies to 3 dimensions. So you can go through and sketch a little picture for yourself here. You got the 3 dimensions. And so if we have the unit vector that terminates at 1, 0, 0, that is vector I. The vector that terminates at 0, 1, 0 is unit vector j. And then the vector that terminates at 0, 0, 1 is unit vector k. So I equals 1, 0, 0. J equals 0, 1, 0. K equals 0, 0, 1. Okay, so you could say, well, how could I and j be this and this? That's context. In 2 dimensions, I is this and j is that. In 3 dimensions, I is this and j is that. Okay, so one of the neat things that you can do with the coordinate unit vectors is the coordinate unit vectors can give us a alternate representation for vector. How does that work? It's kind of neat, actually. If we have vector A is vector A1 comma A2, you can represent that as A1I plus A2J. Okay. If that seems, wait, really? You can check that off to the side, right? So if we have A1I plus A2J, if we know that that I is vector 1 comma 0 and J is 0 comma 1, this is a scalar multiple of 1, 0. So we're going to get A1 comma 0 by multiplying the components by A1. This is a scalar multiple of 0, 1. Oops. So we're going to get 0 comma A2. And then when we add vectors, we add component-wise. A1 plus 0 is A1. 0 plus A2 is A2. Okay, so this gives us an alternate way to go through and represent vectors. So instead of just representing them with the components and these angle brackets, we can instead use I and J. Why do it this way? I don't know exactly. It's just an alternate way to do it. And throughout the textbook, sometimes you'll see this format, sometimes you'll see this format. And so it's just something that you have to get comfortable with, the ability to handle both. Right, so let's just, for a quick example, let's say B equals, I don't know, -1, 4. Then we could go through and represent B as -1 I plus 4J, or you could even leave out the -1 there, just -I plus 4J. Okay, so that is coordinate unit vectors. And then next, normalizing a vector. Okay, so this is, let's say, given a vector, given vector A, if we were to normalize vector A, then we would find a vector U that points in the same direction as A but has length 1. So that's what it means to normalize a vector. It means to go through and create a new vector that points in the same direction as the given vector but has length 1. And the way that you do that is there's a formula for the new vector u. It's equal to a divided by the length of a. So this normalizes a and creates a new vector u that will point in the same direction as a but have length 1. So that may seem a little far-fetched. You can actually go through and verify it. Let's pick out an example. Let's say something simple. We could say a is 2, 1. Then if we were to go through and calculate u would be 2, 1 divided by the length of 2, 1. And you'll recall the length of 2, 1, you do the square root of the components squared. All right, so if we do that, we're going to get 2, 1 divided by the square root of 4 plus 1, which is 5. And then you would, to go through and do this, you could treat this as a scalar multiple of 1 over root 5 and multiply it. So we'll get 2 over root 5, comma, 1 over root 5. All right, so by going through this process, by normalizing vector A, by taking vector A and dividing by its length, we created this. Now the question is, does this point in the same direction as vector A, and does it have length 1? All right, to answer the first question, anything that has the same ratio of these two values will point in the same direction. So we have a 2-to-1 ratio between the x component and the y component. So 4, 2 would point in the same direction as A, 6, 3, 20, 10, and in this case, 2 over root 5, 1 over root 5. This is a 2-to-1 ratio, okay, between these two values. So this does point in the same direction as A. So the only thing left to go through and do is to verify that the length of this new vector is indeed length 1. And if you do length of u, you'll get the square root of the components squared, which would be 2 over root 5 squared plus 1 over root 5 squared. And that equals the square root of, this is 4/5, this is 1/5, and so we get the square root of 5/5, which is the square root of 1, which equals 1. Okay, let me maybe do one more example. So let's say we had vector B, and let's say it had components of -2, 3, and we wanted to normalize vector B. If we want to normalize vector B, we would create a new vector u, which is b divided by the length of b. And so that's going to be -2, 3. Right, that's b equals b. And then here we're going to put the length, so that's the square root of the components squared. So that gives you -2, 3 divided by the square root of 4 plus 9 is 13. And then again, you could just take that root square root 13, make that 1 over root 13, and then do a scalar multiple. So that would be going to give us, -2 over root 13, 3 over root 13. Okay, and again, you can look and you can see this does point in the same direction, and then you could check to determine, to show that this is of length 1. Okay, so that covers everything except for one last fact that didn't really fit in anywhere up to this point, and that is the zero vector. The zero vector is a strange phenomenon. It's a vector that has 0 length. Okay, so this vector is sometimes interpreted to have any direction because of the fact that it doesn't have any length. So it's a kind of a strange vector that doesn't really fit into anything else, but we can go through and we can represent it. The zero vector is represented as 0, comma 0, like that. So it just has 0 components. So it has 0 for the length, and that means that it can interpret it to have any direction because the length is 0. So it's just a dot. It's kind of a strange exception. Okay, so that covers the video on vectors. Thank you for watching. See you next time.